so let's look at solubility equilibria. And in this discussion, what we'll be talking about are certain ionic compounds that are sparingly soluble in water. In fact, in most cases, we tend to say that these compounds are not soluble, but that's not completely 100% true. They do have a degree of solubility, but their solubility is very low. So an example of such a compound is silver chloride. If you add silver chloride to water and you stir it and let it sit for a while, then eventually you're going to have some silver ions and chloride ions present in very small amounts. All right. And we can write down an equilibrium expression based on the fact that we have this equilibrium set up. And that would be given right here, where the K is expressed as Ksp, and that is equal to the concentration of silver ions times the concentration of chloride ions. And you'll notice that there is no silver chloride term in this equation because silver chloride's concentration does not change. Now, the name given to the Ksp in this particular situation is called the solubility product constant, all right? And this is the constant that exists for compounds like silver chloride, as I said before, that are very sparingly soluble in water, all right? So here's another example, magnesium fluoride in equilibrium with its ions. That's the equation right here, and the Ksp expression is given right here. Of course, the concentration of the fluoride is raised to the second power because you have a coefficient of 2 right here, all right? Here's another example, silver carbonate in equilibrium with silver ions and carbonate ions. The Ksp for this equation is shown here, all right? So basically you can write down the Ksp expression once you know how the particular ionic compound dissociates. Here's yet another example, calcium phosphate dissociating to form calcium and phosphate ions, and the Ksp expression is given right here, all right? Okay, so the dissolution of an ionic solid in an aqueous solution can be predicted. In other words, we can predict whether or not there'll be, if you have two ions that would make a precipitate, potentially, you can determine whether or not the concentrations are sufficient in order for the precipitate to form. So if the Q is equal to, or I should say less than Ksp, that means that there's no solution. There's no precipitate form, I should say. It will be an unsaturated solution. If Q, so no precipitate is formed. If Q is equal to Ksp, that means that the solution is saturated, and therefore, when you get to Q is greater than Ksp, that means that the solution is supersaturated, which means that you'll have the spontaneous formation of a precipitate. So we can make some predictions as to whether a precipitate will form depending on the relationship between Q and Ksp, whether or not Q is greater than Ksp. This table here basically gives you a list of Ksp values for different compounds. A more comprehensive list is given in the table that I've posted in Canvas under the files link. If you go to files, and I think if you go to the folder that is labeled tables and you click on that, then you'll see one of the documents there, which will be a PDF document, which is basically a list of the a comprehensive list, a more comprehensive list of different ionic compounds and their solubility products. All right, and as you can see, these numbers are very small. In fact, I think the largest number here is, let me see here, 2.4 times 10 to the minus 4 for lead-2 chloride, which is a very small number. And then, of course, you can get some extremely small values, such as nickel-2 sulfide. Its value for Ksp is 1.5 times 10 to the minus 24. And these numbers just basically reflect the fact that these compounds are very insoluble in water, all right? Okay, so some definitions here. The molar solubility is the moles of a solute dissolved in 1 liter of a saturated solution. And then you have the solubility, which is the number of grams of solute dissolved in 1 liter of a saturated solution. So the units of molar solubility is moles per liter, and the units of solubility is grams per liter, right? And we can use these values once we determine what they are to determine the Ksp, or we can do the reverse. And what we see here on the screen are two flowcharts. The first one showing you basically that we start, if we know what the solubility of the compound is, then we can determine the Ksp by first determine the molar solubility, and then based on that, determine the concentrations of the cations and anions, and then using that to determine the KSP. Or if you're given a KSP, you can do the reverse. You can find the solubility of the compound, all right? And we're going to see some examples of this shortly. In fact, here's the first example. It says, what is the solubility of silver chloride in grams per liter? So, of course, this is the equilibrium system for the silver chloride um, in equilibrium with its ions. And the KSP value, of course, you'd have to look that up. It's 1.6 times 10 to the minus 10. So we set up our ice table. So initially, we would have no ions at all. We don't have to concern ourselves with the silver chloride because, of course, its concentration doesn't change. However, the change that will occur here is that as you go from the initial state to the equilibrium state, the concentration of silver and chloride will increase. Now, we don't know what that is, but we're going to call it S, right? So the change in the concentration of silver ions is plus S, and the same is true for the chloride. That S will be equal to the solubility because basically, whatever the amount of silver chloride that goes into solution mole-wise, that would be the same as the concentration of silver ions and the concentration of chloride ions because of the 1:1:1 ratio between the silver chloride, silver ions, and chloride ions. So therefore, at equilibrium, this would be the state of affairs. The concentration of silver ions would be S, the concentration of chloride ions will be S. So it's all a matter now of plugging these terms into the KSP expression for silver chloride, and that simply gives you S squared. So therefore, to find S, which is the solubility, molar solubility, we find the square root of KSP, and that works out to be equal to 1.3 times 10 to the minus 5. But we're not finished yet because this is the molar solubility. What the question is asking for is the solubility in grams per liter, right? So basically, S would be the solubility, which is equal to the concentrations of the ions, but the solubility of silver chloride in grams per liter will be given by this calculation here. We take the molar solubility and multiply it by the molar mass, right? Which of course you can get from the periodic table by adding up the molar masses of silver and chlorine, and this would be the molar mass conversion factor here. And when you work this out, you get your answer, which is equal to 1.9 times 10 to the minus 3 grams per liter. So that's basically how you would calculate the solubility of a compound like silver chloride in grams per liter once you know what the KSP value is, right? Okay, this is just showing you the units canceling. Okay, now, of course, as you can imagine, for different ionic compounds, you can have different KSP expressions because of the mole ratio differences that occur between the anions and the cations. So, for example, in the case of silver chloride, this is the expression here that we discovered in the previous example. In the case of barium sulfide, this would be the expression. In the case of silver carbonate, however, this would be the expression, of course, because you have two silver ions here, which is reflected in the 2 here as the exponent here for silver ions in this expression, and so on and so forth. Additionally, you can determine what the expression for the cation and anion is in terms of S. So in the case of silver chloride, S being the solubility, of course. So in the case of silver chloride, both of them will have the S value. In the case of barium sulfate, the same, and that's because of the 1:1 ratio between these two. However, in the case of silver carbonate, it would be 2S for the cation and S for the anion, and so on and so forth for the others. So all you have to do now is plug the S terms or the 2S terms, whatever, into the KSP expression, and you'll get different KSP expressions in terms of the solubility. So it all depends on the compound. And of course, if you know the molar solubility, you can easily calculate the solubility product or vice versa, all right? And I think there may be some examples of that. Okay, let's look at this example. Not an example of calculating the solubility. This one is an example where you can actually predict whether or not a precipitate is formed when you add two solutions that could potentially form a precipitate. So in this case, we're adding sodium hydroxide to calcium chloride, right? So in this solution, there are 4 ions present: sodium hydroxide, calcium, and chloride. So the question is, which one of these will come together, or which two of these, I should say, will come together to form a precipitate? Now, the solubility rules would tell you that calcium could potentially come together with hydroxide to form calcium hydroxide. So the solubility rules, by the way, there's a table in Canvas, again, located in the files link, under the files link. You can find the solubility rules there that would help you to make these kinds of predictions. So basically, the only possible precipitate that would be formed would be the calcium hydroxide, right? So next thing we have to find out is whether or not Q is greater than KSP, all right? So what is Q? Q would be equal to the concentrations, the initial concentrations of calcium, which is 0.100, times the concentration of hydroxide squared. In other words, this equation right here. So all we have to do is plug these numbers into this equation, and we get 1.6 times 10 to the minus 8. And then what we have to do is compare that to the KSP. The KSP is equal to 8.0 times 10 to the minus 6, which is obviously greater than 1.6 times 10 to the minus 8. So basically, Q is less than KSP. If Q is less than KSP, that means that no precipitate will form under these conditions, all right? So that's basically a question which involves making predictions as to whether or not a precipitate would form given the amounts of the different ions that is present according to the question, all right? Okay, here's another one. Again, has to do with precipitation formation. In this particular case, we call it selective precipitation. So basically, you have two ions present in a test tube, all right? Namely the bromide ions and the chloride ions. And you're adding silver ions, which would form, could potentially form both silver bromide and silver chloride, all right? So there are two equilibriums that will take place. You have the equilibrium between silver bromide and its ions, the KSP of which is 7.7 times 10 to the minus 13. And of course, the KSP expression is given right here. KSP is equal to the concentration of silver ions times the concentration of bromide. And then we can rearrange this to solve for Ag plus, the silver ions, because that's what the question is asking for. And that would be equal to 7.7 times 10 to the minus 13, which is the KSP value here, divided by 0.020, which is the molarity of the bromide ion, and you get this answer, right? So basically, you're going to need at least this concentration of silver ions to precipitate the bromide ion, all right? Now, we're going to do a similar calculation for the equilibrium between silver chloride and its ions. The KSP you can look up, and you'll see it's 1.6 times 10 to the minus 10. And this is the KSP expression. We rearrange this to solve for concentration of Ag plus, and then we plug the numbers in, and we get 8.0 times 10 to the minus 9. So that represents the concentration of silver ions that would be needed to precipitate the chloride ions. So to answer the question, what concentration of silver is required to precipitate only silver bromide in a solution that contains both of these? The answer is this. The concentration of silver ions must be greater than 3.9 times 10 to the minus 11, but less than 8.0 times 10 to the minus 9, right? So the concentration of silver ions must be greater than this because that's what we calculated here for the silver bromide. This is the concentration of silver ions that would be at the bottom or the minimum where just before precipitation takes place. And this is the concentration of silver ions that would exist just before precipitation of the silver chloride occurs. So therefore, this would be the final answer. Okay, we're going to stop here for this video, and then we'll move on to a discussion of the common ion effect, which we talked about before, but in relation to the solubility of sparingly soluble ionic compounds. Okay, until next time.